but there is also space meaning, so it's not just, it's about what's the technical concepts that this means. So x numbers up to x about x over log x of n should be prime. And this is an asymptotic thing, it gets better for large values. If you want to know how many primes there are up to 100, do you know what amount count now? If you want to know how many primes there are up to a billion, this is a reasonable estimate. Okay, so it's a better estimate for large values of x. So what I'm writing about is a proof. So pi of x is x over log x plus an error term. And then you show that this error term is how much smaller than this important. So if you prove the Riemann hypothesis, which is one of the most famous kind of unsolved problems in mathematics, we will get better information about this kind of approximation about that error term. So we strongly suspect that there's a thing to check, conjecture in the mathematician. But it needs to be true, but can't yet prove. Proving the Riemann hypothesis was a very good way to understand that. The Riemann hypothesis is great, I'm not going to tell you about it right now. it's just one prime, the cases where they're many should be roughly evenly split. If you assume you don't have a standard conjecture, if you assume a strong enough problem that nobody can do, let's be clear about this, then Maynard and polymath and Chang and so on leads to better results, like there are many S primes that by like 12, or even 6 if you assume enough. So your way of solving this problem is going to be to make progress in how much standard conjecture. Unfortunately, that's very difficult, but mathematicians do difficult things all the time. You work on things that are easy and people are making progress. So 2 is going to be really difficult. It's sort of completely clear there are technical reasons. It's sort of understood to some extent why 2 is difficult. So really, for the many why it's difficult, just 2 is a really hard problem. Mathematicians getting a lot closer, and every time mathematicians get a bit closer, we understand a bit more about how primes behave. We have some new techniques to apply. So there's lots to keep working on there. You can go home and have a look at the Polymath blog, the wiki, and the league table, see you can get involved, right? You might need to learn a little bit more maths before you get involved. But why not? So I thought I would leave you with something to think about as a warm-up before you get to proving to a primes conjecture. Because I've got no idea whether the primes conjecture will be proved. I sort of believe it will be. I'm inclined to believe that it's a true statement, and I believe the mathematicians will prove it. I have no idea whether that will be next year, whether it will be in 30 years' time, whether it will be 150 years' time. I've got no idea. Maybe it will be one of you. Who knows? Here's your warm-up problem. So, I talked about twin primes, like 3 and 5, and 5 and 7. These pairs of primes that differ by just 2. So 3, 5, and 7 is like 2 pairs of twin primes glued together, right? There's sort of 3 numbers with spacings of 2 each time. So my question for you is, are there any more triplets like that? And I think that's a good point for me to stop. Thank you very much. What happens if you put bed? Sorry, what do you... Yeah, so nobody's going to come along and say this big fat check or something. So proving the twin primes conjecture will be a really exciting moment. So the person who does it will go down in the history books as having proved this very famous old problem. Somehow, mathematicians are very excited when people solve problems, but they're excited by seeing what the solution tells them about more mathematics. So what was exciting when Andrew Wiles proved Fermat's last theorem was not so much that Fermat's last theorem was true. I mean, that's great, but what was exciting was that his proof led to all sorts of more mathematics solutions that he used to prove Fermat's last theorem, and led to a whole kind of industry of mathematicians saying, oh, I wonder whether I can take this idea that he had and apply it to this other problem. What does this piece of work that he's done in the course of his proof tell me about this other thing? So there are going to be all sorts of consequences. Whoever comes up with a proof of the twin primes conjecture, which might be one person, it might be some massive online collaboration, it's then going to be really exciting to see what comes out of that. So knowing the twin primes conjecture is true is great, would be great, but it's also what can we do with that? And there are prizes in the mathematical community, and it seems possible that possibly the twin primes conjecture might get a prize if it's one person or a group or whatever. But it's much more about what does this tell us about mathematics? How can this tell us more about prime numbers? That's enough incentive to work on it. Yeah. How do you say what you're willing to assume? That's a good question. So you want to assume as little as possible. Ideally, you only use things that you already know to be true. The best possible scenario is that you take lots of theorems that people have already proved, and you put those together along with your own ideas and deduce something. So you only start assuming other things if you really have to. And I mean, sometimes it's just so people, it becomes clear if only when you're doing hypothesis for truth we can prove this. Then somebody else might come along and say, actually, look, you've had some really fantastic ideas. That's great. I can see a way to get around that assumption. So it's not a disaster to promise people when you say, suppose this thing is true. And if you say, suppose the hypothesis is true and then prove some stuff, and somebody then comes along and proves the hypothesis is false, that doesn't mean that what you've done is wrong. It just means that you can't use the hypothesis to deduce it. So yeah, I mean, when you're doing your homework, you have to be a little bit careful that you don't assume something your teacher wants you to do. But it's a well-established way to make progress. What would be the consequences if we knew this? What could we do? So when people make conjectures, they usually have some reason for thinking it's true. So when people were counting primes up to 1 million or 1 billion or whatever, they're making a guess for how that function pi of x behaves. That was based on some kind of ideas, but that wasn't a proof. So you don't just say, well, suppose the following random thing is true, then I can do some stuff. You sort of want to write out something you've got some reasons to think might be true. That's why you come up with a conjecture. So I mentioned there are reasons to believe why the twin prime conjecture is plausible, but you don't have to have a proof when you say, when people say, suppose the Riemann hypothesis is true, then ... That's not because they have the outlines of a proof of the Riemann hypothesis. It's because they've got other evidence from other places for why it might be true, but that's not a proof as such. So yeah, but it's a good question. You don't want to just kind of assume any old thing and then see what the consequences necessarily. Yeah, that's a good question. To the best of my knowledge, the real-life applications of proving twin primes conjecture are currently non-existent. So I'm completely unapologetic about this because, to me, it's really important that some mathematicians, are working on problems because of the intrinsic interest of the problem. Because within the context of pure mathematics, making progress on these problems is really important. Of course, there are mathematicians whose work does relate directly to real-world problems. I have lots of colleagues in Oxford who are busy working on things that have immediate applications in engineering and biology and finance and so on. But it's really important that we do these things as well because of the unforeseen consequences. So the classic example is cryptography. Maybe you're not old enough to have a credit card, I don't know. So when I'm using my credit card on Amazon buying another exciting maths book, I'm typing in my credit card number, I want Amazon to read the credit card number, and I want the baddie along the way to read my credit card number because then they can use my credit card details to buy their own maths books, right? That would be a bad thing. So I need some cryptography there. One of the standard techniques used for encrypting data with online shopping is based on mathematics that goes back to Fermat in the 17th century and Euler a little bit later. They weren't doing it because they were interested in online shopping. They weren't even doing it because of the cryptographic application. They were doing it because they were really interested in properties of whole numbers, in structural relationships about the whole numbers. Centuries later, somebody came along and said, look, this is fantastic, we can take these tools from pure mathematics and apply them. It's very hard to predict what those applications might be, or which things will turn out. So maybe the twin primes conjecture in the future will have some application. Maybe it won't, but maybe the understanding developed in the course of proving the twin primes conjecture will lead on to something. So for me, it's really important that some people are doing that sort of blue skies, pure mathematics, just because it's really fascinating, because we really want to know the answer, as well as people looking for applications.
question, at various points I'll be stopping, and the talk will go much better if you come up with lots of them. Okay, so I used to work at CERN. I did a 2-year job there, research job, a postdoctoral research associate it's called, before I came back here to Cambridge. And as I'm sure you're all aware, you've seen on the news, there was a big discovery at CERN that was announced a year or two ago, and that's the discovery of the Higgs boson. That really is huge news. That's going to be in history books for millennia to come, and it was very exciting. So what I'm going to do is talk to you a little bit about that. I can't resist telling you about the Higgs boson. I'm also going to tell you about dark matter and why the Large Hadron Collider at CERN might be able to tell us something about the dark matter. Okay, so I'm very lucky. I'm a theoretical physicist, what they call a phenomenologist. So that means I care about data, I care about what's going on in the experiment, but I don't sit there with a screwdriver trying to make it work because it would all be a bit and I wouldn't be able to get it back together again. And so I test models of the early universe and of how particles interact, and I suggest how the experiments might look for new particles, how they should sit their data in order to find them, and the interesting properties which they should measure. So I spend a lot of my time thinking about fundamental particles, smaller than an atom, and they're tiny, right? And but I spend some of my time thinking about the universe, which is about as big as you can get. And so, that sometimes happens within a day. I have to shrink my mind and then, grow it. And it reminds me of Alice in Wonderland, where, you drink a potion, you go very small, and you eat a mushroom, and you grow very big. So I want you to come on a journey with me to the very small and the very large. Okay, so this is just going to set the frame for the main topic, which is dark matter. So this, I'm going to show you, is a simulation of a galaxy just like ours. So each one of these white dots represents a star, just like our sun, and they're all rotating around a spiral galaxy. And okay, we're getting to about a billion years now, so obviously it's sped up a bit. And they rotate around the centre of mass, mainly just due to Newtonian gravity and inertia and the usual thing. And okay, so when we look out at other galaxies than ours, we can measure the speeds at which these stars are going around the centre, coming from the bottom of the light that are given off by the stars. And we can use standard gravitational theory to predict how fast they should be going. Okay, it should be a very basic science question. Okay, you need to know how much matter is there. So, but you know roughly the mass of the star. So within say 20% or so, you can guess the distribution of matter through here. When you look at that picture and you compare the predictions using gravitational theory to what's measured, what you find is something doesn't add up. Something very fundamental. The stars around the outside are going way too fast compared to the theory. And so something has got to give. And maybe our theory of gravity is wrong, or something else. And the problem is, many people try to tinker with gravity, tinker with Einstein's equations and even Newtonian gravity to try and make this picture add up with observations. But the problem is it's very difficult to do that while keeping all the things that we know about where the theory of gravity works, for example in the solar system, and actually even in the universe as a whole. It's very difficult to keep that working while make the galaxy spin faster around the outside. So what we think is probably going on instead is that there's some extra matter there that you can't see, it's invisible. So it's transparent to light, and against the nighttime sky it looks dark, and that's why it's called dark matter. And indeed, very probably we have dark matter in our galaxy, and even more probability, with the same probability, there's a wind of dark matter going through us right at the moment. So this stuff is fleeting, it hardly interacts with matter at all except by gravity. Most of it would go straight through the Earth. So according to the estimates, you should have about 20,000 times the mass of a hydrogen atom with dark matter in you at any moment. And the wind of it going through you is going at about 400 kilometers an hour, astonishingly. So obviously, if this stuff is really around, it's not like a standard wind or standard storm. So what we're going to do is frame these questions: what is dark matter, and how does it behave, and how can CERN help us answer those two questions? So we're going to go on a journey to find that out. And how are we going to do that? Well, we're going to go down the rabbit hole by shrinking ourselves. So what I want to do is just get our minds into the kind of distance scales that we're talking about. So if we shrink ourselves down to the size of a fly, you might get worried because it's looking hungry and it's carnivorous. So that's about a centimetre, say. If we shrink ourselves down to a millimetre, now we're at the size of about the fly's eye, and all these compound segments in it. It's kind of amazing. So when we shrink ourselves down another 100th of a millimetre, you'll be able to see the bristles in between the segments of the fly's eye. Further down again to a millionth of a millimetre, if we could shrink ourselves that much, we'd be able to see the strands of DNA in the fly's eye. So around the outside of the helical structure, we have these spheres, which are artist representations of atoms, of course. And so if we zoom in on one of those, 10 millionth of a millimetre, this is a representation of an atom. It's completely wrong, not just because of the face, right? The central bit should be much smaller, etc. But I've drawn a baseball one because that particle is a photon, and that's going to help us answer our questions that we posed at the start. So very good. So in order to do that, what I need to do is take our minds back to 1 second after the beginning of time. Okay, so 1 second after the Big Bang. 1 second after the Big Bang. The Big Bang is very quiet, by the way. So 1 second after the Big Bang, everything in the universe, observable, anything you can see today, the observable universe, would fit in the atmosphere above the UK. Okay, the atmosphere of the Earth. So of course, if you try and squeeze all of that, all those stars and everything, into that small space, they don't exist as stars and planets anymore. They are it's an extremely hot, dense plasma of gas. So it's particles flapping around at very high temperatures. And if we think about the particles in this primordial soup, as it's called, then we get then we have energy just knocking around. The particles are all just bouncing against each other, and that's what makes these particles. jigging around and bouncing off of each other. So at this point, I'll take any questions that anyone has. Yeah. So the question is, where did the plasma come from? I think the answer to that is no one knows yet, for sure. The universe was born with space that's expanding very quickly, and time which is also expanding very quickly, and lots of energy in it. And we don't really know where that energy came from. If you read Stephen Hawking's book, The Brief History of Time, you'll know that in the 80s he solved some of the equations of the evolution of the universe, and it required an injection of energy. And he said, well, whatever that is divine being, right? So he was being consulted by the Vatican because he thought he had an argument for the existence of a divine creator. But since then, he found a solution which could happen randomly and didn't require a divine creator. I don't think he's advising the Vatican anymore. But the answer is no one knows. That's an open question. Yeah.
If, obviously, first of all, in terms of orbiting galaxies,
the question is, are galaxies orbiting anything? And the answer is yes, they are. You have clusters of galaxies, and the galaxies move within those clusters, and you have superclusters, which are clusters of clusters of galaxies, which again move. So on all distant scales, stuff's going on and things are moving. Yeah. Okay, let's carry on for a bit. So, we go back to our primordial soup, and at the moment, 1 second after the Big Bang, everything's too hot, and protons can't even exist yet. You've got 3 particles that make up their quarks. They're just rattling around themselves. But as the universe, the Big Bang happens and the universe gets large, the space in between the particles gets larger, and the gas cools down.